Hi, this is the MA 166 Spring 2024 exam number 1. So starting with question 1. Question 1 asks, find the center and radius of the sphere defined by the following equation. So x squared plus 2x plus y squared minus 4y plus z squared plus 12z equals 8. So first, what we want to do is we want to think about what the general formula of a sphere is. So that formula looks like this, which is x minus a squared plus y minus b squared plus c minus z squared equals r squared. And a, b, c, and r are constant, where a, b, c is the center of the sphere and r is the radius. So we can find the answer to this question if we take the equation that they gave us in the problem and convert it to this form. So how we're going to do that is we have to complete the square for each variable, so for x, y, and z. So to complete the square, so if we complete the square for x squared plus 2x, x is the first term in the parentheses, because we just take the square root of this x squared term. And then we have 2x. To take care of this 2x, what we're going to do is we divide 2x by 2 times the coefficient of the number we put here. So 2x divided by 2 times 1 would be 2. Sorry, not 2, 1. So to complete the square, we get x plus 1 squared. And then we can verify that this is correct by expanding this, and we get x squared plus 2x, and that matches what we had before. And this is important for later, but we also get a plus 1. Okay, so now if we similarly complete the square for y squared minus 4y, we get y minus 2. And then we get, for the z term, we get z plus 6. And we complete the square in the same way here. Basically, the square root of y squared is just y, so that's the first term. And then we divide, for like y, we would divide negative 4 by 2 times 1 to get negative 2 here. And then same thing for z. Okay, so if I factor everything out, I can just double check. So minus 4y plus 4 plus z squared plus 12z plus 36. So an easy mistake over here would be to just say that this is equal to 8. But that's not true. What actually happened, so everything I'm underlining in red over here is equal to 8. But we also have these additional constants, which would change the constant that goes on the right-hand side here. So I'm going to actually erase this. So to balance things out, essentially, and get the correct equation that's equivalent to what they give us in the formula, we have to add 1, 4, and 36. Those are the constants we get because of completing the square. And now once we do that, the right-hand side becomes 49. So this means that the center is negative 1. So the center of the sphere is negative 1, 2, negative 6, and the radius is the square root of 49, which is 7. So that means that the correct answer is A. Okay, moving on to question 2. Alright, Question 2 says, given u, that the magnitude of vector u is equal to 3 and the magnitude of a vector v is equal to 5, and the angle between vectors u and v is pi over 3 radians, find the magnitude of u plus v. Okay, and they give us this hint that says that the magnitude of u plus v squared is equal to the dot product of u plus v is equal to u plus v dot u plus v. Okay, so let's start from the hint. The hint essentially tells us that our answer that we want to find, the magnitude of u plus v, is equal to the square root of the dot product. The dot product u plus v dot u plus v. Okay. So the formula for dot product, there's two formulas that we can use. The first formula states that, so for vector u dot v, let's say that we know the coordinates of these each vector. If we know the coordinates, say it's like u1, u2, and v1, v2, the dot product is equal to u1 times v1 plus u2 plus u2 times v2. Yeah, and that's one formula. The other formula states that u dot v is equal to the magnitude of u times the magnitude of v times cosine theta. And in this case, we can't use the first formula because we're not given the first, we're not given the coordinates of any vectors, so we have to use the second formula. So if we use the second formula, we get, actually we don't use the second formula yet. First, what we want to do here is we want to expand out what we're given. So just like normal multiplication, the dot product, we can use the distributive property on the dot product. So if we do that, we get u squared plus v squared plus 2uv. And now we can calculate the, I should clarify, when I say u squared, it's u dot u. So it's u dot u plus v dot v plus 2 times u dot v. Okay, so now we can individually calculate each of these three dot products. So u dot u is equal to the magnitude of u squared times the cosine of the angle between u and u. So now because these two vectors are the same, they're overlapping, which means that the angle between them is 0. So it's times cosine 0. And so we're given that the magnitude of u is 3, so it's 9. And cosine 0 is 1, so u dot u is 1. Same thing with v dot v, that's just the magnitude of v squared times cosine 0. So this is 25. And then now we have u dot v. This is a magnitude of u times magnitude of v times cosine. And in the problem, we're given that the angle between u and v is pi over 3. So that's where we plug that in. So that's equal to 3 times 5. And the magnitude of, the value of cosine pi over 3, we can use the unit circle to calculate that. That would be 1/2. So this is equal to 15 over 2. And yeah, so going back to how you know cosine pi over 3 is 1/2, either you memorize it or you can draw out the 30, 60, 90 triangle. And so if we know that this hypotenuse is 1, like it is in the unit circle, then that means that this longer side would be root 3 over 2, and the shorter side is 1/2. So for cosine, we use the x over the radius, so that's how we get 1/2. Okay, so now we have our 3 dot product values. We just have to plug it back into our equation. So we get 9 plus 25 plus 2 times 15/2. That is equal to 9 plus 25 plus 15, which is equal to the square root of 49, and this is equal to 7. So our final answer for question 2 is C. Okay, so problem 3 says find the orthogonal projection of vector u onto vector v, where vector u is equal to 2, 1, 1, and vector v is equal to 3, 0, 4. Alright, so first, let's just go through what they mean by projection. So suppose we have our vector u and our vector v as such. We can find the projection by draw an altitude, essentially, a line that makes a right angle with the vector v from the tip of u down to v. This line segment makes a right angle. This endpoint over here, this vector that I drew in red, that is the projection of u onto v. Okay, so to find the value of this vector, we only have to do 2 things. We just need to find the direction and the magnitude. So the direction is quite easy. Since we're finding the projection of u onto v, this is directly on top of v, so it's pointing in the same direction as v. So the direction is v, but more importantly, we want to think of the direction in terms of the unit vector. The unit vector is a vector that has a magnitude of 1. So right now, the magnitude of v is 5. We can find the magnitude by taking the square root of the square of each of these terms. So to get the unit vector, all we have to do is divide vector v by the magnitude of v. And this gives us the unit vector that points in the direction of v. This is important. Having the unit vector is important because to find the value of this projection vector, all we're going to do is we're going to multiply the magnitude of that vector times this unit vector. Okay, so the magnitude is the it's a harder part. So we can find the magnitude of this vector by using trigonometry. Let's say that the angle between these 2 vectors is theta. That means the length of this vector is equal to the magnitude of u times cosine theta. And that's just using SOHCAHTOA. This adjacent over hypotenuse is equal to cosine theta. Okay, so the magnitude is cosine theta. We have the direction. So the value of the projection vector is equal to u, magnitude of u divided by the magnitude of v times cosine theta times the vector v. Okay, so there's not a lot we can do with this right now, mostly because we don't know the value of theta. However, this portion up here looks very similar to the formula for the dot product of 2 vectors. So the dot product of 2 vectors is equal to u dot v. Dot product, where the dot product is u dot v. This is equal to the magnitude of u times the magnitude of v cosine theta. So right now we have the magnitude of u and we have cosine theta. All we have to do to get this formula is multiply by the magnitude of v again. So if we multiply by the magnitude of v on the top and the bottom, we get that divided by the magnitude of v. Okay, and we can rewrite the top now as u dot v divided by, this would be v, the magnitude of v squared. So now all we have to do is find the magnitude of v and find u dot v. So I gave one formula for the dot product. The other formula states that if the value of u is u1, u2, u3, and the value of v is v1, v2, v3, where those are like the coordinates, the dot product is equal to u1 times v1 plus u2 times v2 plus u3 times v3. So in this case, u dot v equals 2 times 3 plus 1 times 0 plus 4 times 1, and that is equal to 10. Okay. And now the last part is finding the magnitude of vector v. So the magnitude of a vector can be found by taking the square root of the square of each term. So we would take 3 squared plus 0 squared plus 4 squared. And that is equal to 5. So plugging all our values in, we plug in 10 divided by 5 squared times the vector v, and we get 2 over 5 times the vector v. So the answer to question 3 is E. Okay, moving on to question 4. Question 4 says that the area of a triangle with, it asks us to find the area of a triangle with vertices 2, 1, 1, 2, 2, 3, and 1, 2, 2. So, suppose our triangle looks like this. What we can do, first, let's call this point A, this point B, and this point C. What we can do is we can find the value of vector AB and vector AC. So we find this by, to find AB, we would take the coordinates of B and subtract A from them. So we would take, for the x coordinate, that would be 2 minus 2, that is 0. 2 minus 1 is 1, and 3 minus 1 is 2. So same thing for finding AC. Take this and subtract these numbers from that. We get negative 1, 1, 1. Well, negative 1, yes, negative 1, 1, 1. Okay. So now the reason we did this is because we can use the cross product of two vectors to find the area of the parallelogram that encompasses, that is formed by those two vectors. So in this case, we would find the area of this parallelogram over here. So that's the region that I just shaded. And they don't ask us for a parallelogram. They ask us for a triangle. However, the triangle is just half of the area of the parallelogram. So now all we have to do is find the cross product, and the magnitude of the cross product is equal to the area of the parallelogram. Okay. So find the cross product. So okay. So the way we find the cross product of two vectors is by taking the determinant of the matrix where the first row is I, J, K. I, J, K are the unit vectors in the x direction, y direction, and z direction. And then the second and third rows are just the vectors. And now, according to the formula for determinants, this is equal to I times 1, 2, 1, 1 minus j times the determinant of 0, -1, 2, 1 plus k times the determinant of 0, 1, -1, 1. So that's according to the formula. And now finding the determinant of a 2 by 2 matrix is a lot easier. We just take the we multiply one diagonal and we subtract. So we subtract the value of this diagonal that's going right to left from the diagonal that's going left to right. Okay, so basically we have I times 1 times 1 minus 2 times 1 plus, minus j times 0 times 1 minus -1 times 2 plus k times 0 times 1 minus -1 times 1. Okay, and then we get that this is equal to -1 to 1. So this is the value of the cross product. To find the area, again, the area is the magnitude of the cross product. So we have to find the area, so the magnitude of this vector. And that is equal to the square root of each term, each coordinate kind of the vector squared. So -1 squared plus 2 squared plus 1 squared. And that is equal to square root of 6. And remember, the square root of 6 is the area of this big parallelogram. So the area of the triangle is half of that, meaning that square root of 6 divided by 2. So the answer to question 4 is B. Alright, question 5 says, find the area of the region bounded by the curves y equals x squared and y equals the absolute value of x. So for any problem like this, a good starting point is to draw out a diagram of what the problem is telling us to do. So y equals x squared. Y equals x squared looks kind of like this. And then y equals the absolute value of x would look like this. Okay, and that means that the area we want to find is the portion shaded in red here. Okay, so the first thing we're going to do is find out where do these two curves intersect. So it should be pretty easy to see that 0 is one of these points, but we can verify that again later. So the way we're going to find all the points at which these two curves intersect is by setting the two curves equal to each other. So we set x squared equal to the absolute value of x. So that gives us two equations. For x is greater than 0, we have x squared minus x equals 0. And for x is less than 0, we have x squared plus x equals 0. And then if we factor this, okay, so our three solutions are x equals 0, x equals 1, and x equals -1. Okay, so this over here is x equals 1. Okay, now we can get on to the integration part. So another thing we can notice is that to find the total area that we have here that I've shaded, we only need to find the area of one of these regions. Since the two curves are symmetric, the area of this region is equal to this region because both the regions have the same shape. So all we need to do is find the area of this region over here and then multiply by 2. So 2 times the integral of 0 to 1. And what we do is we take x, because in this part over here, the curve y is equal to x is on top, minus x squared. And we do a minus x squared because this region is bounded by y equals x squared on the bottom. So that is our integral. And now all we have to do is find the antiderivative. So using the reverse power rule, the antiderivative of x is x squared over 2. And then using the reverse power rule for x squared, the antiderivative of that is x cubed over 3. And this is from 0 to 1. And then now plugging all that in, we get 2 over 1/2 minus 1/3, 2 times 1/2 minus 1/3, and that is equal to 1/3. So that means that our answer to this question is A. Question 6 says, consider the region enclosed by the line y equals x and y equals x cubed in the first quadrant. Find the formula for the volume of the solid obtained by rotating the region about the x-axis by the washer method. So, as we should do with any problem like this, the first thing we should do is draw a quick diagram. So we have the line y equals x and y equals x cubed. So y equals x is like this, and y equals x cubed is something like that. And what do they say? They say find the volume for the find the formula for the volume of the solid obtained by rotating the region about the x-axis. And the region is this area. It's the area enclosed by the two curves in the first quadrant, and we are rotating it this way. Okay, so now what we have to consider is what is the washer method. So the washer method basically states that we can think of our 3D solid as the sum of the areas of multiple disks. So if suppose we have some kind of solid like this, I'm not going to draw out a solid. Suppose we have some kind of solid, we can visualize the solid as a circle with another circle like cut out of it. So this is our disk, and basically we can find the area of all of these disks, add them up together to find the volume. So for example, in this case, I would take this tiny little strip here, and then if I rotate it, I get one disk, and I could like take another, and then I would get like a smaller disk. And basically I'm going to do this for every single tiny strip in this region to find the volume using the washer method. So that means we need to find the volume of the solid first. So suppose we have this as tiny r, small r, and the larger radius as big R, then the area of this solid would equal pi times capital R squared minus pi r squared. Because pi r squared is the formula for the area of a circle, and basically to find the area of a disk, we take the larger radius, the area of the larger circle, and then we subtract the area of the smaller circle from that to find the area of the disk. Okay, So now we have all the information we need. We have almost all the information we need, actually. The last thing to do is we need to figure out where to integrate from. So it's pretty clear that both our curves intersect at 0. We need to find the other intersection, and that's at the point 1, 1. How we find that is we just set these two equations equal to each other. So if we set x equal to x cubed, we get x cubed minus x equals 0, and then we get x squared minus 1 equals 0. And so one of the solutions is 1. Two of the solutions are 1 and negative 1. It's clear that this point over here is negative 1 because it's on the negative side of the y-axis, the negative side of the x-axis. So this is our intersection here is 1, 1. Okay. So now we're going to take our integral from 0 to 1. We are changing the length of this strip with the x-axis. So we're going to be integrating relative, so our integrand is going to be dx, because the quantity we're changing here is x. That's what's going to, our radius values are going to be relying on x, basically. So now this line will tell us the value of the larger radius, and then the curve y equals x cubed will be the smaller radius, because as you can see with this drawing over here, this aligns with y equals x, and the smaller cut out circle lines with y equals x cubed. So basically we plug in y equals x into this formula and y equals x cubed into here. So what we get is pi times x squared minus x to the power of 6 dx. So volume is equal to this, which means that the answer to question 6 is A. Alright, question 7 says, which of the following integral gives the volume of the solid obtained by rotating the region enclosed by the curves y equals x and y equals x squared about the line y equals 2 by the shell method? Okay, so first thing to do is draw a quick picture. So we have y equals x squared. Okay, that wasn't bad. Actually, I'm going to erase this. Okay. Okay. So this region over here is at the region that we're going to be rotating, and this is our line up here. This is the line y equals 2. We're going to be rotating this way. Okay, so next thing to discuss is what is the shell method. So the shell method tells us that we can think of our solid as a bunch of cylinders kind of that are stacked like on top of each other. So for example, I would consider this tiny, so we consider them as a bunch of cylinders, and then we find the surface area of each cylinder and then we add it up. So for example, I have this tiny strip over here, and then once I rotate it, I'm going to get this cylinder over here, and then all I have to do is I have to find the lateral surface area of this cylinder, and that's going to give me, so I find the lateral surface area of that cylinder, and then I do that for every single strip in this region, and I add up all the lateral surface area of all of those cylinders, and that's how I find the volume. Okay, So what is the lateral surface area though? So the formula for the lateral surface area is 2 pi r times the length, so the length of the cylinder. So okay, so if this is my cylinder, and if r is this radius, this length over here would be L. Okay, so last thing I need is I need to know where do these intersection points occur. And we can do that by setting y equals x and y equals x squared equal to each other. So if I do that, if I set x equal to x squared, I get x squared minus x equals 0, and then I get x times x minus 1, so equals 0. So this point over here, it's pretty obvious, that's 0, 0. And the other intersection point occurs at x equals 1. So this is this point here is 1, 1. Okay. Now I just have to find the formula. I have all the information I need to find the formula. Okay. So like I said, we're going to be changing this, the length of this like line over here is L. And we're going to be changing L as we move up the y-axis. So our integrand is going to be dy. And our bounds for this problem don't change. So it's 0, 1 either way. So yeah. Okay. Now we can, so there's going to be a 2 pi no matter what. We need to find the value of r. We need to find the value of L. So this line's, okay, I'm going to erase all of these here. Okay, so the value of the length of this line segment is L, and R would be the distance from y equals 2 to that line segment. Yep. Okay. So let's find the length of L first. So the length of L can be found. First, what we need to do is we need to rewrite this line in terms of x. So we get x is equal to square root y. So it would be, okay, so this point over here is square root y. This point over here is y. So it would be the square root of y minus y would be the value of L. Because again, this curve over here is y equals x squared. This is y equals x. We can't just use x squared minus x because our integrand is in terms of y. That's why we have to convert y equals x squared to a function of y, and that's why we convert it to x equals square root of y. Okay, now we need to find r, and so the length of r would be 2 minus y. Again, because we're going to be integrating in terms of y, so the length of r will be changing relative to how y is changing. So that means that the volume is equal to the integral of from 0 to 1 of 2 pi times 2 minus y times the square root of y minus y. So that makes the answer to question 7C. Okay, moving on to question 8. Question 8 says, if the work required to stretch a spring 4 feet beyond natural length is 32 pounds, how much work is needed to stretch it 3 inches beyond its natural length? Okay, so for this question, we're going to need the formula for work, which states that work is equal to the integral of force times dx. Okay, and then we also have the equation for Hooke's law, which states that force is equal to K, which is the spring constant, times X. Okay, and then right now they tell us that 32 is the amount of force we need to stretch it 4 feet beyond its natural length. So we can say that 32 is equal to the integral from 0 to 4 of f times dx. And then we can plug in this equation over here for f. We get 32 is equal to k times x dx. And now, since our this number over here is our spring constant, so now we can integrate as usual, and we get kx squared over 2 from 0 to 4. 32 is equal to k times x squared over 2 from 0 to 4. And so if I plug in the 4, I get 32 is equal to 8k, which means k is equal to 4. Okay, so now we're going to do the same thing. We're going to use these two equations now to solve for work again. So work is equal to force times dx, which is equal to, now I know that k is 4, and I want to stretch it 3 inches beyond its 3 inches beyond equilibrium. And so I get 8x squared, 2x squared from 0 to 3 by doing the antiderivative, which means that the answer, once I plug in 3, is 18. So that means the answer to question 8 is E. Okay, moving on to question 9. Question 9 says, a tank has the shape obtained by rotating the curve y equals x cubed about the y-axis with unit in foot. The tank is full of liquid, of which each cubic foot weighs 3 pounds. The work required to empty the tank by pumping out all of the liquid from the top of the tank is given by the formula, and they want us to calculate the formula for the work. Okay, so let's draw a picture. So our tank looks something like this. And they say y equals x cubed, where x is between 0 and 2. So that means the height of the tank is where x equals 2. So if I plug in 2 to y equals x cubed, I get the height of the tank to be 8. Okay, so we can think of work as the amount of force required to, in this situation, we can think of work as the amount of force required to lift a certain piece of water times the height that we need to lift it. So, like, for example, we would consider just the flat circular region over here, and we would find the area of this piece of water, and multiply it by the distance that we need to lift it. Because the formula for work is force times distance. So basically, we need to consider each individual slice of water, each circular slice of water, and then multiply it by the height that that slice of water needs to be raised by. Yeah. So all in all, it all goes back to this formula, even though thinking of slices of water is a little weird. All right, so that means that we're going to be integrating. Since we're emptying the tank out from the top, the value that will be changing in this case is y. So our integrand is going to be dy. We're going to be integrating from 0 to 8. And the two numbers we need, quantities, are the weight, because force is equal to, it's not equal to mass, but it's equal to weight, and they give us the weight in pounds. So we would take the weight times the weight of each piece of water, and times the distance it needs to travel. So let's calculate that now. So first we would find the area of this piece of water. The radius, so the area of a circle is pi times r squared. The radius of this region is, well, we have y equals x cubed. So the radius of this region is x cubed then. But we need to have it in terms of y. So x, so we have to rewrite this formula as x is equal to y to the power of 1/3. And we're going to be using that quantity instead. Okay. So basically, pi r squared, we plug in y to the power of 1/3 instead, and we get pi times y to the power of 2/3. Okay, and the other quantity we need is how much we're raising the water by. So that's easy to see. The value of the distance here is y, what the variable we're integrating in terms of, which means that this distance would be 8 minus y. So we have pi times y to the power of 2/3 times 8 minus y. And there's one piece we're forgetting. That is the mass of the water. So this quantity over here is only the area. We also need to multiply by 3 because they say that each cubic foot weighs 3 pounds. So we multiply by 3 at the front. So our final integral is 3 pi times y to the power of 2/3 times 8 minus y dy, which means that the answer to this problem is E. All right, moving on to question 10. Question 10 says, find the length of the curve y equals x cubed over 3 plus 1 over 4x from 1 to 2. Okay, so for this question, we're going to need the formula for the length of a two-dimensional curve. And that formula, so I'll write it, L is equal to the integral from a to b of 1 plus dy dx squared times dx. So I guess I can go over a quick understanding of like why we do this. So suppose I have some curve and I'm trying to, okay, that's a horrible curve. Suppose I have some curve and I'm trying to approximate the distance, the length of this curve. So I can use the Pythagorean theorem. So this is dx and this is dy. Using the Pythagorean theorem, I get d is equal to this delta x squared plus delta y squared. And then now what I can do is I can I can take out the delta x, and so I get d is equal to 1 plus delta y over delta x squared times dx on the outside. And then you'll see that this looks very similar to this. What I can do is, to find like the overall length of a curve, is I can take tiny little pieces like this of, multiple dx's, delta x's, and delta y's and add them up together. That's what this integral is. And then eventually, if you make your delta x values smaller and smaller and smaller, you come to this formula. That's a quick high-level understanding of how we get this formula. Okay, so now all we have to do is plug in our values to this formula. So let's find dy dx. So if we use the power rule, we get x squared minus 1 over 4x, because we can think of 1 over 4x as 1 over 4 times x to the power of negative 1. And I actually integrated it wrong. It would be 1 over 4x squared, because we multiply the negative 1 out front and we reduce the power, so negative 1 becomes negative 2. That's how we get x squared minus 1 over 4x squared as our integral. Okay, so now just plug in all the values. We have L. Our bounds, A and B, are the bounds that they give us in the problem. So basically the length, the endpoints of the curve. So that's 1 and 2. And we have 1 plus x squared minus 1 over 4 x squared squared. So if I expand that out, I get x to the power of 4 plus 1 over 4 times x to the power of 4 minus 1/2. And now if I add up everything, I get x to the power of 4 plus 1/2 plus 1 over 4 times x to the power of 4 dx. Okay, and so you'll notice that for this problem, they want us to actually get to a number, so a formula alone is not enough. So somehow we have to find the square root of this, and that's not impossible. You'll notice here that this expression looks very similar to this expression, except instead of a plus 1/2, we have a minus 1/2 over here. And this is the square of x squared minus 1 over 4x squared. Noticing that pattern, we can realize that our expression over here is equal to x squared plus 1 over 4x squared. So like almost exactly identical to what we have for the expression of dy dx, except instead of a minus 1 over 4x squared, we have a plus 1 over 4x squared, and that means that the x forward term and the 1 over 4x forward term, 1 over 4 times x to the power of 4 term don't change, but our minus 1/2 becomes a plus 1/2 because we have a plus over here. So that makes things easy now. we just need to find the antiderivative of x squared plus 1 over 4 times x squared. And then using the reverse power rule, the antiderivative of x squared is x cubed over 3, and the antiderivative of 1 over 4x squared is negative 1 over 4x. And that's very similar to what they gave us in the original problem, from 1 to 2. And now I just have to plug in all these values. So if I plug in 2, I get 8 over 3 minus 1/8 minus, now I plug in 1, I get 1/3 minus 1/4. And now if I solve for this, I should get 59 over 24. So the answer to our problem is C. Alright, moving on to question 11. Question 11 says, find the volume of the solid S described below. The base of S is the region bounded by the parabolas y equals x squared and y equals 2 minus x squared. And B, the cross-section perpendicular to the base and parallel to the y-axis are squares with one side on the base. Okay, so let's draw a picture, like always. We have y equals x squared and y equals 2 minus x squared. It's not the best drawing, but this is our region over here. And suppose we lay it out flat like this. We're going to take squares. Let's use a different color. We're going to take squares like this. As I said, the base, the cross-section perpendicular to the base. So the base of these squares is perpendicular to the volume of the solid. Okay, so to find the area of this shape, what we can basically do is we can find the area of each of these little squares and then add them up together to find the total volume. So the length of these of the bases of these squares would then be changing relative to the x-axis. So we're going to have dx as our integrand, and then the area of a square is given by s squared. So we just have to find the side length of the square and then square it. Okay, now we just have to find what is the value of s. So suppose this would be like an example, side length. So this top curve is 2 minus x squared, and this bottom curve is x squared. So that means the length of this line segment would be 2 minus 2x squared. We just subtract x squared from 2 minus x squared to get this. That's how we find that. Okay, so we're almost done. Last thing to do is find our bounds. Where do we start for x? What is the upper and lower bounds? We do that by setting the two equations equal to each other. So if I set x squared equal to 2 minus x squared, I get 2x squared minus 2 equals 0, or x squared minus 1 equals 0. Which one's factored? It becomes this. So our bounds are x equals -1, x equals +1. Now I have everything I need to solve for b. Okay, -1, +1. I'm going to expand this out. I get x to the power of 4 minus 4x squared plus 4 dx. And then now I'm going to find the antiderivative. So using reverse power rule, I get x to the power of 5 over 5 minus 4x cubed over 3 plus 4x. And this is from -1 to 1. Okay, now I just plug in all 1 and -1 into this expression. So if I plug in 1, I get 1 over 5 minus 4/3 plus 4. And then minus, now I plug in -1, -1/5 plus 4/3 minus 4. And then if I solve for this, I get 64 over 15. Okay, question 12. Sorry, before moving on, that means that the answer to question 11 is D. Alright, moving on to question 12. Question 12 says, evaluate the integral from 0 to pi over 2 of x squared times sine x. Okay, so we can use two strategies for this problem. Either integration by parts or tabular integration. So I'm going to do the hard way first, because tabular integration is basically a shortcut for integration by parts. So integration by parts states that we can use this formula. The integral of u dv is equal to uv minus the integral of v du. Okay, so integration by parts is useful anytime we have logarithms, polynomials, or trig functions, or exponential functions. And in this case, we have both a polynomial and a trig function. And we can use that formula to a formula to do integration by parts. Yeah. Okay, so how I usually start is I write down u, v, and then du and dv. So the hardest part about integration by parts is figuring out what you're going to set as u and what you're going to set as dv. So notice that one thing that can make integration by parts hard is that you have another integral over here. And so if you mess up, you can make your new integral, like this over here, more complicated, and we want to avoid that. So to make it less complicated, what we want to do is take advantage of the fact that du is in our new integral. So we need to set u equal to something that can be simplified once it's integrated. So I think for this problem it's pretty clear that we're going to set u equal to either x squared or sine x. Suppose I set u equal to sine x. If I set u equal to sine x, du becomes cosine x. V would actually become x cubed over 3, which is more confusing. So we don't want to do that, because then our new integral would be of x cubed over 3 times cosine x, and that's way more complicated. So we set u equal to x squared, that makes du 2x, and then we set dv equal to sine x. So this is our u dv, and the antiderivative of sine x is negative cosine x. So we get that the integral of this is equal to uv, so negative x squared cosine x, minus negative cosine x times 2x. So I'm going to simplify that. Negative 2x times cosine x. Okay, so this is simpler. It is better. And I'm also going to put this negative sign up front. This is better, but it's still not something we can easily integrate. So what we can do is actually use substitution again to simplify this integral over here. Okay, now if we do that, it's the same process and the same process, and even we use the same intuition too. So instead of setting u equal to cosine x, we're going to set it to 2x, because that means du is simplified to 2. dv becomes cosine x in that case, and that means the antiderivative of cosine x is sine x, so v is sine x. Okay, and so now if I do all that, this expression over here becomes negative x squared times cosine x plus 2x sine x, 2x sine x plus the antiderivative of v du, which is 2 sine x. So you'll see we did achieve our goal. We found the antiderivative successfully. Not the antiderivative. We found something that we can find the antiderivative of. So now we just need to find the antiderivative of this quantity. That's pretty easy. It's just, oh, I made one mistake. There should be a minus sign here, because that's what we have in our formula. That's what we have in our formula. It's minus v du. Okay, so basically all of this is equal to negative x squared times cosine x plus 2x times sine x. And the antiderivative of sine x is negative cosine x. So this is equal to 2 times cosine x. Okay, so that's our antiderivative. Okay, so before solving for this, I'm also going to go over the tabular integration method, which is way simpler. So we have x squared and sine x. Tabular integration states that we can split our expression to be integrated into two parts. So I'm going to draw a table, and I'm going to write d dx on one side, and then draw an integral on the other. So we start off with x squared times sine x, and you can use this method basically only when you have one part of your expression is as a polynomial. So if you have a polynomial times another expression, that's a good indicator that it's possible to use tabular integration. So what I'm going to do on the left-hand side, the side that says d dx, is I'm going to integrate. I'm going to find the derivative. So x squared becomes 2x, 2x becomes 2, and then I get 0. I'll stop there. On the other side, I find the antiderivative. So the antiderivative of sine x is negative cosine x. The antiderivative of negative cosine x is negative sine x. And the antiderivative of negative sine x is cosine x. Okay, so what do I do now? Now, what I'm going to do is I'm going to multiply on these diagonals that are going from top to bottom. So from up to down, x squared times negative cosine x, 2x times negative sine x, and 2 times cosine x. And I multiply this product times positive 1. Then I multiply by negative 1, and then positive 1. So what you're going to do is you're going to multiply like this, and then you start off with positive 1 and then just alternate negative 1, positive 1. This method could go on like super long if it wanted, and you just multiply negative 1, positive 1, and keep going. Okay, so I get x squared times negative x squared times cosine x, 2x times sine x, and then 2 times cosine x. And to find the antiderivative, I just add up all of these quantities that I get, and I get negative x squared cosine x plus 2x times sine x plus 2 times cosine x. And that is our antiderivative. You'll notice it's the exact same as what we got before. So last step is finding our actual quantity. They tell us to evaluate it from 0 to pi over 2. Oops. So I just need to evaluate this from 0 to pi over 2 and plug things in. So okay, so if I plug in pi over 2 first, I get so I have negative pi over 2 squared times cosine pi over 2 plus pi times sine of pi over 2 plus 2 times cosine pi over 2. And all of this subtracted by plugging in 0. So if I plug in 0, this first expression is 0, the second expression is also 0, and then I get plus 2 times cosine 0. Okay, and so now cosine of pi over 2 is 0, sine of pi over 2 is 1, and then again cosine of pi over 2 is 0. So these two, don't have to worry about them basically. And so that means, and then over here, 2 times cosine of 0 is, cosine 0 is 1, so this is equal to 2. Basically, that means that this whole expression evaluates to pi minus 2. So the answer to question 12 is D.